Assalamualaikum warahmatullahi wabarakatuh. My name is Ahmad Khairudil Habib Mazin, and you can call me Khairul. My matrix number is 241110904. Today I would like to do some discussion about topic 4.6, the Reynolds transport theorem. Okay, in this lesson, it will show the analogy between the material derivative and the Reynolds transport theorem, or we can call it RTT. And then the second one, it will discuss the purpose of the RTT, and then it will show the form of RTT, including a various simplification. Okay, so for introduction, in this topic, we can learn about the two things. The first one is a system, that also called as a closed system. It is a quantity of matter of fixed identity. So the closed system is mean there is no mass can cross a boundary system. And then the second one is a control volume, and also called as an open system. Is a region in a space that chosen for study. So the control volume or open system is mean is allow a mass to cross or flow out from the system boundary. So we can look at the example figure 454. There is two methods of analyzing spraying of deodorant from a can. So we know that the can is a system. This is because the mass cannot flow up or cross the boundary, or it is mean there is a system over there. And then we follow the fluid as it move and deform. This is the system approach. So there is no mass cross the boundary, and the total of the mass system is remain fixed. So this is before we spray the deodorant. And then the second one, we consider a fixed interior volume of a can. So this is the control volume approach. The mass cross the boundary. So whenever we spray the deodorant can, so the spray mask is flow out, so it mean that this is the control volume approach. So the control volume approach is not concerned at all with the deodorant that has escaped from the can. This is because the mass of the control volume is decreased during the process, while its volume is remain constant. So the relationship between the time rate of change of an extensive property for a system and for a control volume is expressed by the Reynolds transport theorem, RTT. So we can look at the figure 455. The Reynolds transport theorem, RTT, provide a link between the system approach and the control volume approach. So we look at this example. There is the system and there is the control volume. So the RTT is linked between both of this approach. We look at the example figure 456. A moving system which hatch region and fixed control volume shaded region in the divergent portion of a flow field at the time t and t plus interval time. The upper and the lower bound are streamline of the flow. So when we look at the figure, there is the green shaded that we mentioned as a section 1, and the shaded region that we mentioned as section 2. So the section 1 is inflow during interval time, and then the section 2 is outflow during the interval time. So at the section 1, we also have a V1 uniform speed, and at the shaded 2 we also have a V2, and then at the section 1 we also have a control value at time t plus interval time. CV remain fixed in time, and then we also have a system and a control volume at time t, and then the between section 1 and section 2 we also have a system at time t plus interval time hatch region. So when we let capital B represent as any extensive property such as mass and energy that we known as a scalar, or momentum that we know as a vector unit, and then the small b can be the responding intensive property. So small b is equal to capital B divided by m, that we know as mass, the property B per unit mass. And then our goal is to find the relationship between B system, capital B system or small b system, property of system for which we know the conservation law, and capital B control volume and small b control volume, property of control volume, which we prefer to use in our analysis. So the result is shown below. So for fixed control volume, it's mean non-moving and non-deforming. RTT fixed CV is equal to these equations. So this part is equal to change of capital B system due to the unsteadiness, and this part is represent to the change of capital B system due to the movement speed of fluid across the control surface. So for the second equation, the alternate RTT fixed CV, we change the definition and integration to this, since the control volume is fixed and the order of the integration or definition does not matter, so it means these two things is same. So for the non-fixed control volume, so it means the moving or deforming, the RTT non-fixed CV equation we will type like this. So the difference between the fixed and non-fixed is at the V. So the difference from both of these equation is we replace V by the VR in this version of RTT for a moving or deforming control volume. So what is the meaning of VR? VR is the relative velocity. So the velocity of the fluid relative to the control surface, which may be the moving or deforming. So the relative velocity is equal to VR equal to V minus V control surface. So what is the relationship between the material derivative and the RTT? So when we look at the figure 465, the RTT for the finite volume integer analysis is analogous to the material derivative for the infinitesimal volumes differential analysis. In both cases, we can transform from the Lagrangian or system viewpoint to an Eulerian or control volume viewpoint. So it means the material derivative is used to transform from Lagrangian to the Eulerian description for the differential analysis, but the RTT is used to transform from system to control volume for integer analysis. So when we look at this figure, the differential analysis is the Lagrangian description is changed between the d over dt, it means the differential analysis to become the Eulerian description. However, the RTT is the system analysis is changed to the control volume between the RTT that we mention it as a integer analysis.